And I'm Sachin Chugh, Associate Director and Energy and Hydrogen Lead of ARUP India. ARUP is a global multinational consultancy dealing in all facets of sustainable energy solutions. So today I am going to speak on this very important topic. The roots of which I would be carrying from my some of the work which I carried in my earlier organization, that is Indian Oil Corporation Limited, and try to paint a new canvas of what are the new opportunities and the challenges before all of us in the form of engineering and taking forward the kind of plans which our country or per se the globe is looking at to drive a green hydrogen economy across for multiple applications. So I'll just share my slides uh, and continue with my talk. Yeah, I hope my slides are visible. Nishant, can you just confirm?
We see a slide, Sachin.
Okay,
Just
thank
go
you
ahead.
very much. Thank you very much. So, as we transition from the policy formulation to the practical implementation of green hydrogen initiatives, the significance of engineering becomes increasingly critical. The urgency of this shift is actually driven by the pressing need to address the environmental degradation. Yet, we face the formidable challenge of navigating an industry which doesn't has any historical precedent. Now, unlike the other renewable energy technologies, hydrogen presents a unique complexities. It's a blend of multiple challenges. Its properties require extensive monitoring systems, and that involves the integrate integration poses significant hurdles, and the supply chains are constrained. So this means that we have to have the right kind of addressals at this point, at this moment, and therefore the my topic of engineering the future of hydrogen becomes pertinent at this point of time. So the presentation has been designed to present, to cover the realities of this endeavor, paired with a call to action, encouraging the collaboration with the various stakeholders, including us, to find the right path forward. And the company from where I belong to, ARUP, is a renowned name in the realm of engineering, celebrated for its creating the architectural marvels in vibrant cities and leaving an inedible mark on history. Our commitment to sustainability, especially since COP26, sets us apart from the crowd. Now, driven by the ambition to deliver the unprecedented advantages in the energy sector, we are poised to lead the charge towards meeting the environmental challenges. So currently, we are present in about 62 countries where our renewable energy projects are underway. We are having around 900 renewable energy projects that are currently under execution. And with a strong workforce of 18,000 plus engineers and scientists and the technical experts, we are here in India to provide the global consultancies with the local presence. And if you see the entire value chain, we are into the entire spectrum of energy, not only hydrogen, but the other forms of distribution, including the offshore winds, the transmission and distribution, the nuclear, and whatnot. So here we are here in India to start a fresh chapter, which actually is going to pave the way for most of the things which are going to you are going to see and witness in the hydrogen economy. Now, coming on to the topic, I'll be covering few fundamentals and before driving on to the engineering aspects of hydrogen. Uh, there are some properties of hydrogen which already all of us have been discussing at various forums. And I would not dwell upon these properties per se because they have been talked a lot. But yes, just for a minor reference, the density of hydrogen is about 7% of water. It is when it is in liquid form, it is about 7% of air when it is in gaseous form. The energy density per se is about 2.4 times the methane. And when we take forward the compare it with in the liquid form or the volumetric efficiency, volumetric energy densities, it's about 2.9 kilowatt hour per meter cube, which actually calls for a lot of compression or liquefaction if we have to transport it to a longer distances. Flame speed, particularly when we talk of the combustion of hydrogen, it is 6 times more than methane. It has its pluses as well as the demerits. The ignition energy is very less, therefore it requires a very small source of ignition in order to actually catch the fire. But yes, the flammability limits are so wide that yes, the safety threats actually belong to hydrogen, and those have to be properly addressed. Now, these are all the properties which have been discussed at length, but I would be talking of certainly not so commonly discussed properties like the expansion ratio. Now, it is actually the difference in the volume between the liquid and the gaseous hydrogen. It can be when the hydrogen is expanded from the liquid to the gas, it actually takes up about 848 times the volume. And when we are considering the compressed hydrogen, which is expanded to a normal atmosphere, the volume which would be taken up by hydrogen would be about 240. And that's where the entire mechanism of handling the hydrogen itself is going to be quite challenging, and this is where the word is really struggling. Now, coming on to the diffusivity, the diffusivity of the gas is referred to, it actually is the ability to spread or diffuse through the medium. Now, typically, the diffusivity is measured in terms of the diffusion coefficients, and we can see on the screen that hydrogen has a very high level of diffusivity as compared to natural gas. Now, the when we talk of 0.61 centimeter per square as the diffusivity, this means that once it is released in the air, it is going to spread very fast. It is going to actually mix with the air very fast. Now, this is one of the important properties which actually control the mechanism of designing certain systems of how to handle hydrogen when we are using it in practical terms. Now, permeability, again, it's the ability of the gas or the hydrogen to pass through a barrier or a membrane. Particularly, we are talking of the electrolyzers and the fuel cells. We can see that the 10 to 1000 barrel, these are the units. But when I compare to the permeability of hydrogen with respect to methane, so it is about methane carries a permeability of about zero point 0.1 barrel. So we can understand that how fast it can permeate, and therefore the devices like the smaller clearances in terms of various systems, we can have significant challenges around designing those aspects. Now, electroconductivity of hydrogen is it has an added property of lower electroconductivity, so that the flow or the agitation of hydrogen gas or liquid, it generates the electrostatic charges that can result in the sparks. Now, when we are talking of transportation of hydrogen in the pipelines, this property becomes very important, and we have to take care of these aspects while designing certain systems. Next is the octane number. We are habitual of seeing the research octane number normally when it is related to the combustion of any gas inside the engine. And uh, the difference, there is another octane number which is called as a motor octane number, and the difference is termed as the sensitivity of the engine. Basically, this difference is desired to be very low because we want it actually relates to the condition of the engine switching from a condition of high speed, high load to a low speed, low load kind of a condition. And if this sensitivity of the engine is less, this means that the transition is going to be very smooth. And but unfortunately, hydrogen, although it has a very high research octane number, it actually has very low motor octane number, which actually makes it a little difficult fuel in terms of handling as far as the engine combustion is concerned. Uh, quenching gap. It's basically the distance for the hydrogen which the flame can travel. So we can see that it can be good or it can be bad, and there are certain safety aspects which become favorable when we are talking of lower quenching gap of hydrogen. That is because it is going to extinguish before reaching a certain distance. The efficiency of the combustion process is going to increase because it is not going to carry too much energy along with it. But it has certain demerits attached to it because the combustion stability, because in some of the combustion systems, particularly those involved in premixed hydrogen air mixture, a smaller quenching gap can lead to combustion instability. And then it also calls for a limited range. So when we are thinking of uh, handling the colorless and the odorless gas like hydrogen, the role of sensors become very important. But the distance between the leakage point and the sensors, they can actually suffer because of this lower quenching gap, and therefore it becomes imperative that the right kind of planning is done before we select the spaces where to install the flame sensors while dealing with the hydrogen systems. So, if I come to the landscape of green hydrogen production technology, electrolyzers are one of the preferred choices, and all of us are fully aware of what are the technologies which are prevalent in the market. Be it the alkaline electrolyzers, which are the old horses as far as hydrogen production is concerned. So people are indicating that they have the lower upfront cost. They do not need any critical raw materials, and per se they are quite reliable. But yes, there are certain disadvantages, like they are not flexible in terms of load following, and they have a limited output pressure, and therefore if the end application calls for building up of the pressure or the storage of hydrogen, then there might be certain problems. The PEM electrolyzers, now they are not the new things in the market, but yes, the kind of scales which we are looking forward in the industry. Earlier, PEM electrolyzers were not designed for those scales, but yes, they do come up with certain advantages, like we can have higher pressures as the output from the PEM electrolyzers. The flexibility to the load following is great, and that's where when we are targeting applications other than the industrial applications like automotives, definitely these kind of electrolyzers are going to be of they are going to add much more value as compared to other counterparts. But yes, they are ridden with certain problems, and one of them is the cost associated with the precious metals which revolve around platinum, particularly for the hydrogen oxidation and the oxygen reduction reactions. Now, the alkaline has a new phase which probably combines the benefits of the conventional alkaline technology as well as the PEM electrolyzers, and they are the anion exchange membrane electrolyzers. Particularly, they are highly flexible, and they come up with a compact design, and no critical raw materials are required. But this particular technology is at a very nascent stage, and therefore require a lot of research in order to exhibit the true sense of its advantages at a scale at which the industry is looking at. Solid oxide high temperature electrolysis, particularly well suited for the industrial applications, when we can combine it with the waste heat available from the processes. It's quite resilient to the impurities because while operating at higher temperatures, it doesn't require any purification methods, and that's where the sensitivities with respect to its operation, as far as the impurities is concerned, can be an added advantage. But yes, since they operate at 750 to 800 degrees centigrade, the long cold start times actually are going to be one of the deterrents, and that's where, when we are looking for continuous generation of hydrogen, this can be the technology to reckon with. Having said that, again, this technology is getting matured and would take some time before we can scale it up to a certain level. So when we, as an industry, we are making a decision Which electrolyzer is to be selected? There are multiple parameters which can actually help us navigate this particular challenge. And those are that what are the downstream applications, whether it is the only one requirement is there, or we are thinking of clubbing multiple requirements into one. What is the quality of hydrogen which is required? Is it going to interfere with the process catalyst of the downstream processes? Like, for example, on the right side, I've given an example that the alkaline electrolyzer may contain the traces of potassium hydroxide. And particularly when we are talking of some applications of green hydrogen in the refineries, this particular KOH can interfere with the hydrotreating catalysts, or usually deployed in the refineries in order to get highly pure fuels, which likes of the likes of gasoline and diesel. And therefore, this particular KOH, the traces can deactivate the catalyst. They can it can cause the performance reduction. Even at the ppm level, it can interfere with the catalyst ability to facilitate the desired reactions, leading to lower conversion rates and reduced effectiveness. Also, this can result in the formation of deposits, which can cause catalyst fouling, or the increased pressure drop because of this accumulation. And under the alkaline environment, it can actually cause certain structural changes in the catalyst, or the leaching of the metals. So therefore, becomes very important that what technology we are choosing, it should be aligned with the downstream application of hydrogen per se. Turn down ratio I discussed, very important parameter. It would not only make it a more reliable function technology, but also the turn down governs that how effectively we are able to use the asset, and that has a very high level of impact in terms of uh, uh, our the costing of the complete project. Degradation over lifetime is one of the important aspects, because durability is one of the factors which can impact the cash flows at a later stage of the electrolyzer life. Temperature and heat balance, again, the requirements of the additional heat, if it is there, or how the heat has to be removed if it is a low temperature electrolyzer, that becomes imperative in as far as the design of the complete system is concerned. And last but not the least, the footprints. We are talking of the current densities. So each of these technologies are going to operate at different current densities. Therefore, the constraints in terms of the availability of space are also one of the factors that how these technologies are to be chosen. So, like I said, the choice of electrolyzer technology is going to actually vary based on how is the load variation, the end process application, whether the mobility is an integrated part of the complete value chain or not, the purification levels which are required, the degradation, and the cost. The high temperature electrolyzers per se, they are said to consume lower amount of energy, because in this particular graph, if you can see, if you the more you are raising the temperature, the lower electrical energy is going to be consumed in order to split the water molecule. Now, however, this also the higher temperature electrolyzers also calls for the heat demand, and if this heat is not available in the form of waste heat, then it the comparison can be redrawn, and therefore it becomes very important that what is the end application. So per se, the total energy consumption, which includes both electrical and the thermal energy, a solid oxide electrolyzer generally consumes less total energy compared to PEM electrolyzer. However, the higher temperature operation of solid oxide electrolyzers, they allow them to use where the thermal energy can be effectively utilized, thus reducing the electrical energy requirements for improving the overall efficiencies. Now, coming on to a little bit deeper topic of water. I know it has been touched a lot, but somehow when we go for the process engineering or the design of the hydrogen plants, we tend to ignore one side of the complete narrative. And that's where I call it as a water energy nexus. That is because the kind of topic which we are discussing today, the water is required to produce energy, and particularly for generating this energy, the water is required, and for producing that water you require energy because water is not available in the form in which it is required. So when we deep dive into the complete narrative as a feedstock into the electrolysis process, this is one dimension to it where water is directly converted into hydrogen and oxygen gas. And the second form is as a cooling fluid to remove the heat generated in the process. When we talk of the efficiencies of the electrolyzers, per se 75% or 70%, in particularly in this particular range, the remaining energy has to be withdrawn from the process, and that's where the cooling fluid becomes very important. So there are various mechanisms by which this cooling can happen. Undergoing the evaporative cooling is one of the methods of cooling. However, there are alternatives such as air cooling, and that could also be used. Now, when I come to process water, the when a current is passed through the electrolyzer and the hydrogen is split, we need the as a feedstock, we need the process water. But as a cooling water, is used for maintaining the heat balance of the process. It is also used in the compressors to maintaining the compressor temperature. And while we are talking about the policies around the world, we are not considering the additional requirements which might cause several constraints and may change the complete dynamics of the project investments, which can result in uh, under designing the water systems. And later on during the life cycle of the or during the operation of the plant, we may end up requiring more water because of the cell degradation. And if incorrectly designed, the plant would definitely operate, but the durability is going to suffer. So this is where the proper engineering design becomes very important. Now, question is, how much water does hydrogen actually need? So when water requirements per se are highly variable, we cannot have a pinpoint rule that 1 kg of hydrogen would require about 9 to 10 liters of water. So when analyzing the entire hydrogen value chain, you know, we have to understand what is the source quality of water, what is the treatment method, what are the climatic conditions under which the electrolyzers are getting installed, what is the hydrogen production method, which electrolyzer are we going to use, the cooling method, and the hydrogen carrier conversion process in case we are thinking of translating or deriving the derivatives of hydrogen, like ammonia and all that. So in this particular slide, you know we have compared, we at ARUP have compared that how much water exactly it would be required. Now it can also turn down that the system efficiency, the actual amount of the water can vary depending upon the efficiency of the electrolyzer, its temperature of operation, the weather conditions. But this value may only be 10% of the total water demand, which is for which the plant has to be designed. The main consideration has to come from the cooling water requirements. So there are multiple methods. Like I said, we here in this particular study, actually we assess three different cooling methods. Once through cooling method, evaporative, and the air cooling method, and saw that each may be suited to certain location and climatic conditions. Now when we add any water used in the cooling medium to that water demand, it actually gives a completely different narrative. So the water requirement can be somewhere between 15 to 70 liters of cooling water for the electrolysis and the gas purification processes. This is because the evaporative cooling has a high water requirement and high consumption rate due to losses in evaporation, particularly when cooling towers are getting used. And I'm talking of the plants which are going to be bigger in size. So, and this is well suited to a wide range of conditions, but it can definitely result in greater water losses, especially when we are talking of the operation of the electrolyzers uh, in the dry zones, in the dry climatic regions, than in the wetter areas. So meanwhile, evaporative cooling suffers from this disadvantage. The air cooling, it does not use any water, which may suit certain conditions and locations at best, but it is more expensive to implement and therefore require more energy input. And then any further processing, such as liquefaction, as indicated, or conversion to ammonia, it would exert additional cooling demands. Another aspect which is missing is the load is not considered due to the cell degradation and over a period of time. So how much is that? Probably, we can discuss in the coming slides. And continuing our discussion, so basically, if we see the requirements as far as the process is concerned, but the variation in the quality of the water can also result at how much groundwater would be required. Now this particular study is not customized for India, but we did it for Australia, and you can see on the graph that it actually depends upon what is the source of water, and therefore the energy requirements, energy spent on purification or desalination of water, or the actual volume of the water requirement would depend upon the raw water quality. Now water sources such as seawater, they require a lot of treatment, and because a lot of water is actually rejected as a waste. Now if we see depending upon various kinds of requirements, a minimum of about 23 liters to about 94 liters of water can be raw water, would be required. Now in India particularly, if the mandates come for the refining sector or the fertilizer sector as far as green hydrogen is concerned, many setups which we are talking of are going to be in the landlocked areas. And I am assuming that the hydrogen transportation is not going to happen. We are going to generate or produce and consume hydrogen at the same location. So with so many constraints around the withdrawal of the groundwater, are we thinking of transporting hydrogen from the coast, which is not a viable option, or transport the desalinated water towards the hydrogen plants inside the landlocked production centers? That is a question which maybe the industry need to answer. So we at ARUP have did propose some business models to recover the minerals also from the discharge or the brine of the desalinated plant. And this process, which is called as the brine mining, aims to extract the valuable minerals and compounds from the concentrated brine produced as a byproduct of desalination. Now, technologies are available, but again, what is the application? What is the cost? These are the things, and what is the durability of the thing, of the complete system? These are the things, which we need to understand before we embark upon any such solution. How the properties do vary, I'll not go into the detail, but yes, the pH levels or the TDS levels or the conductivity, they all influence the durability of the electrolyzer, the efficiency of hydrogen generation, and along the time span. And therefore, what appears to be correct at this stage, as far as selection is concerned, may not appear, may not be showing those many results, those many favorable results in at a longer date. And therefore, right kind of interventions are needed when we are designing the complete plant. Now, when I talk of the emission intensity, particularly how much emissions are getting generated out of hydrogen production. We compared multiple pathways, but I'll only be sticking to the green energy pathways or green hydrogen pathways. And when we see biomass coming into picture, because of the net negative CO2 cycle, it appears that biomass is more favorable as far as emissions are concerned. And by the way, when you are looking at around 17.6 number kg of CO2 coming as a number being emitted by the solar electrolysis, this particular emission intensity is based on well to tank kind of studies, which does take into account the mining of the materials required for the solar panels, and therefore a lot of emissions are getting generated at that for that particular process. But coming back to the topic, when we are considering biomass as one of the potential sources for green hydrogen, we have to see and negate the double accounting, which probably can be done because all of us are considering that biomass is going to absorb that particular CO2 or would have absorbed that CO2 during its life cycle. But again, when we are talking of some kind of bindings on us, as far as the creation of CO2 sink is concerned, we would have accounted for those emissions at an earlier date. And the second thing, like I discussed, the manufacturing emissions related to the production of the solar panels or the mining of the material need to be considered in order to arrive at some realistic numbers. Apart from these emissions, there are some unattended emissions, which we call it as fugitive emissions. And per se, these emissions have now become very familiar. Have become very common in the discussion forums, especially when we are talking of the methane emissions. But I wanted to highlight a word of caution here, because are we, as far as hydrogen industry is concerned, are we moving towards the methane way? And why I am touching this topic is because irrespective of any production technology revolving around green hydrogen, particularly pertaining to the electrolyzers, there are cycles of venting during startup and shutdown of the electrolyzer systems. And because they are designed to prevent the buildup of an explosive mixture of hydrogen and oxygen, as we are aware that the lower explosive limit of hydrogen in oxygen is about 4%, as we discussed it earlier. And to provide a factor of safety, the hydrogen concentration is driven down to less than 25% of this limit. So this means that at startup, any air within the cathode side of the system is vented, which is shown in this particular figure. Now, similarly, this particular cycle is followed during the shutdown also, just to avoid any kind of safety threats. Now, when we discussed it with various OEMs, it was indicated that the loss of hydrogen, and by the way, this is neat hydrogen which is getting lost during the purging process, is about 0.1% of the total hydrogen produced. So for basically, so when we say 0.1%, but we start multiplying it with the volumes of hydrogen which are going to be generated or which are being envisaged, the number may swell and it may look very large. So this is how, that's why we have to take these things into consideration. And then there are other processes also which are happening within the electrolyzers or the fuel cells, and that is related to hydrogen crossover, particularly onto the oxygen side. And if we go by some of the numbers which are have been reported, we may end up losing about 0.05 to about 0.15% of hydrogen, of the total hydrogen being produced. And then downstream, when we are thinking of getting the desired quality of hydrogen, again the purification processes are to be handled, and that's where we may end up losing about 2 to 5% of hydrogen. And when we are talking of thermochemical processes like the biomasses and all, this particular loss may further increase. So this is how we have to assess that how much hydrogen emissions are going to be there in the ambient. And not today but tomorrow, definitely there would be some restrictions and some limits on these emissions also. So per se, if I combine these three aspects, the total hydrogen loss can range from somewhere around 2% to about 5.5% of the total value. And like I said earlier, the number may look large when we are thinking of tons and tons of hydrogen for the industry. Coming on to the the CO2 standard, which most of the countries are now in process of setting. Some have already done so. India also has embarked upon this, and we are right here. As This particular standard has been recommended, uh, not more than 2 kgs of CO2 per kg of hydrogen is allowed, which can qualify the so-called produced hydrogen as green hydrogen. Now, when we back calculate this, this means that uh, considering the combination of the grid electricity as well as the renewable energy. So this calls for about 95% of grid and 5% of 95% of renewable energy and 5% of grid. Uh, but when we see the dedicated plants, this might be possible considering the fact that there is a wide variation between the generation capacities of the plant and the installed capacities of the renewable energy. Uh, this particular number may be looked at little bit ambitious. And why I indicate that is because uh, while while at 2 kg we are allowed about 5% of the grid, if we increase this number to about 3 kgs of CO2, and by the way, this is only the production number which is there. Most of the countries have gone with the well to wheel numbers, which are a little bit higher than this particular number. And it does make sense to include other aspects of hydrogen value chain also, particularly when we are talking of transportation of hydrogen for export purposes. And so if we take little bit of liberty in this particular number, what we can do is, what we can meet is that we can use little bit more grid. Now the questions may be asked whether this cost would increase or not, depending upon what is the cost of the grid electricity versus vis-a-vis RE power. But it would give little more flexibility in terms of ensuring the right kind of reliability for the hydrogen plants. Also, if I extend this narrative to the combination of the renewable energy and the methane reforming, because we are targeting compressed biogas also as one of the feedstock for the production of green hydrogen, the existing steam methane plants can be used for CBG production. It can give us some kind of leverage to use the existing plants and therefore avoid the asset redundancy. There are therefore couple of things again we need to target, and clarifications might be required whether this hydrogen outlet is at a normal temperature pressure conditions, or it is at a standard pressure conditions. What is the outlet pressure? Because the CO2 emissions are going to change with respect to the outlet pressure of hydrogen. So that's why I call it as a comparison between the megajoules and the kgs. What should be in the denominator? Because the calorific value of hydrogen decreases with the impurities, and therefore we have to be little cautious in terms of exports, because difference in the units which other countries are following, it may become one of the conflicts at a later stage. uh, Energy, as far as energy is concerned, we can see that the green hydrogen pathways are going to be very near to the blue ones or the gray ones, and therefore we need to see that how seamlessly we can provide the energy to the complete system. Uh, in a nutshell, if I dive down into the complete hydrogen value chain, we can try to analyze the various criteria based on what are the sites available for the production of hydrogen, the characteristics of renewable hydrogen systems, what is the correlation between the electrolyzers and the power plant and the battery energy storage systems and their parameters. Therefore, we need to apply the multi-criteria analysis and then preparing the cost tool and deciding the best possible algorithm. And these are the kind of services, or these are the kind of analysis which would be required in order to arrive at the right numbers as far as the least cost of hydrogen is concerned. Now, if if we further detail it up into the optimization work, we have multiple sources of renewable energy. Now, again, there are capacity factors associated with the electrolyzers, and then there can be different types of electrolyzers. So we can have different set of numbers coming from different set of criteria, and this analysis becomes very important, particularly when the experience of the other parts of the globe is concerned, and we can leverage those things while deciding the hydrogen plants for India. uh, Meeting the ends, again, we are here talking of, if the call is for production of the derivatives like ammonia, we are talking of two complex systems coming together and getting themselves integrating. So this interfacing actually induce the variabilities which are there in the RE system and the downstream molecule production. So therefore, the dynamic models, which are not static, dynamic models for process optimization over a lifetime are required to arrive at the right numbers. The customized model for stack durability and the balance of plant design and the system efficiency, are required. The beginning of life performance of the cells and the end of life performance of the cells is going to be hugely different. These kind of criteria should be there, and the specific models of durability of the electrolyzer stack and the battery energy systems are required, which can actually lead us to the right number of FID, making the financial decisions, followed by the pre-feed and the feed studies. So particularly in refinery, I talk of multiple cases, multiple scenarios. Those have to be properly understood when we are targeting the integration of green hydrogen in the refinery, and see that how the process optimization can take place, as far as the resource optimization can also take place, leading us to the least cost of hydrogen. So in a nutshell, some of the risk factors which are automatically associated with the hydrogen plant, they include the water purification and management, the variations around those things. They constitute the technical risks, the power management, the variation in the performance of the electrolyzer stacks and all, thermal management, and the gas processing. So combined all, so these risks are going to have a lot of impact on the final project cost, and therefore some judicious decisions are to be taken with the right kind of discussions and consultancies. So why we need these accurate analysis? Because of the simple fact that there are two aspects to it. One is the capex and the opex, and we all know that the opex particularly influence the cost of hydrogen in a much larger manner. But is it so difficult, to analyze it? A simple tool can they do it? But our experience says that when we are scaling it up from something which is available at a pilot stage, the scale exponents come from experience. Like, for example, the Haber-Bosch process, the economy of scale ceases to exist after a certain scale. We cannot assume it as a perpetual scale of deriving the economies of scale. So no standard correlation exists between the electrolyzer capacity and the ammonia plant. Model sensitivities are very complex. There are risk premiums which are needed to be factored into the complete value chain. The locational challenges of the greenfield projects, they can have significant impact on the projects, and the delivery timescales, demand uncertainties, production cost uncertainties, and subsidy regimes, they are all going to influence. That's why we require to have very accurate analysis done as far as the operations are concerned. So I'll just, as far as the technical aspects are concerned, I just uh, uh, put forward some of the experiences which we carry as ARUP across the globe. You name it, and we have it in terms of the hydrogen requirement, the hydrogen projects. across the globe, and we have touched each and every facet of the hydrogen value chain, be it on the derivative side, or be it on the transportation side, or on the refueling station sides. All the applications which are linked to it, like carbon capture or direct carbon capture, or the likes of this production of the synthetic aviation fuels, or the green ammonia and the green methanol derivatives. India per se is going to act as the center of excellence in green hydrogen and derivatives for ARUP, and we have had the experience of touching each and every aspect of the hydrogen value chain through multiple projects revolving around hydrogen hubs, ammonia production and infrastructure, and leading to its transportation and exports, uh, ammonia storage, sustainable aviation fuels, green steel, again e-methanol and carbon capture and utilization technologies, leading it to the application side of mobility, assisting the clients with the gigawatt factory, setting up of the gigawatt factories, undertaking a lot of techno-economic studies as far as the automotives are concerned, and leading to the hydrogen pipelines, the transportation of virgin hydrogen or the blended hydrogen in the pipelines, existing pipelines as well as the new pipelines, hydrogen trains, and guiding and navigating the clients for designing the offtake arrangements in order to have the minimal risks involved in the complete process. So I'll just pause here and invite all the questions yeah, from the audience. And once again, thank you very much for your patience hearing.
Sachin, thank you very much. I think that was a bag full, a lot of different topics you touched, and I think we've had a very diverse set of questions as well. But before we start answering all the questions, I want to let the audience know that you can switch on your mics if you have questions. We'll begin by taking some of the questions in the chat. There's a question from Vijita Sharma, Sachin. It says, apart from KOH, what other waste products are generated during green hydrogen production and how are they managed? How does green hydrogen production impact water usage and availability? And what steps are being taken to minimize the environmental footprint of green hydrogen production? Maybe you can start with the first one.
Yeah, so particularly the kind of technologies which I mentioned, it's the alkaline electrolyzer. And alkaline electrolyzer is based on the fundamentals of using an alkali to drive down the redox reactions, and therefore anything which is alkali can be used. But primarily, I touched KOH is because that is the most common electrolyte which is used at a commercial stage, and that reference was there. But yes, if it is not KOH and it is a different electrolyte medium, we have to again go back to the drawing board and assess that how the end application for which green hydrogen is intended is going to be influenced by the traces of those that alkali in hydrogen gas.
Sachin, I have a follow-up question on that. For potassium hydroxide, what are its uses otherwise? Is this a complete waste product that's being generated, or are there applications we can use this for?
We are not talking of a great amount of KOH in this particular hydrogen generation system, Nishant. It is about primarily our feedstock is again going to be water here, and it's the traces which we are more concerned about. So when we are migrating from a conventional alkaline electrolyzer to the likes of the anion exchange membrane electrolyzers, again, the percentage of KOH in water is going to be further reduced. It is going to reduce drastically. And therefore, so per se, no valid case or business case for using the KOH, or taking it out kind of thing, because the consumption is not going to be great. But it is about the topic which I was discussing was to understand the impact of the traces on the downstream application.
Now, in what downstream applications does this really be a concern?
See, as far as my experience goes, I particularly assessed it from the refinery side. But yes, there should be some of the cases where we have to see that other applications like the fertilizers, because it all depends upon what are the catalysts which are being used in the downstream application where this green hydrogen is going to be used. So these things are going to be vary depending upon the catalyst recipe.
Wonderful. I know that there is the R&D team from Ashok Leyland on the call. If there's somebody here, if y'all could switch on your cameras and mic and come online, might have some questions for y'all. Well, I'm not sure if they're still on the call, but we'll move on to the next question, Sachin. How does green hydrogen production impact water usage and availability?
The availability of green hydrogen per se is going to be based on how we are devising our policy framework around that, because we have to accept the fact that at this point of time the generation is going to be costlier, and that's where a very fine tuning of the policy narrative as well as the optimization in terms of the complete hydrogen plant design is concerned. It can bring down the cost, but having said that, at this point of time it is much more costlier than the conventional gray hydrogen.
Wonderful. And your last question, Vijita, which was on the environmental footprint of green hydrogen production, I think this is something the industry is waking up to. We're all aware, and I know there's no guidance officially from the ministry on this, but we can expect something to come along once the green hydrogen standard for India is being introduced. But I've shared a quick link in the chat where I've given a link to the green hydrogen standard we developed years ago, and you'll see some guidance on water use and management there. Moving on to the next question. This one's from Shuple Gupta. Is the emission from solar electrolysis also accounts for the mining of metals used in the electrolyzer?
It all depends upon what are the boundaries of our study. uh, Really speaking, if we leave the aspects from qualifying the definition and take bring forth the complete environmental narrative into the complete picture, it is the well to wheel assessment which is required. We might be producing or mining the material, the metals at some other geography, but it doesn't mean that they are not accounting for the emissions. When the focus is on complete well to wheel, definitely these factors have to be considered. But when the focus is only on the production, then these factors can be ignored.
And I think most standards across the world, they do not include these emissions from the mining
Yes,
of metals. So,
e-
it's, I think this will come into play when you're looking at total life cycle emissions
absolutely.
under different regulatory regimes. Next question from Chintan Mehta. Does it mean gas-based SMR and solar electrolysis-based hydrogen have similar emission implications and hence different degrees of greenness?
I would not say same degree of emissions, but definitely the electrolysis is going to be a better pathway as far as overall emissions are concerned. But one thing we must see out is the difference comes from the fact that in SMR the CO2 emissions uh, are particularly coming out because of the feedstock, and in case of the electrolyzers, the CO2 emissions are actually getting generated because of the production process of the materials which are going to convert the electricity in the sunlight into electricity. So, but the difference can is great, and it is not less a difference to qualify both of them under the same category.
The next question from Shuple Gupta is venting hydrogen during startup compulsory? Will the downstream system not take care of the impurities generated?
No. So it is not about the impurities getting generated. It is about multiple other factors. Also, like I said, yeah, since uh, it is a combination of hydrogen and oxygen system. There is a tendency that certain hydrogen molecules they cross over the membrane and come on the oxygen side. So if we don't purge these systems, there will be the accumulation of hydrogen and oxygen on the same side of the electrolyzer, which may reach a certain flammability range, and that's why purging is required. So it's one aspect is about the purity, another aspect is about the operability and the safety.
Very, very interesting, Sachin. I think with the safety aspect being included, it should be a norm within most operations. Now, another question from Vijita Sharma: how is India addressing challenges related to grid integration and storage of hydrogen?
Yeah, so that's where I touched that it's not a small topic to straight away say that this much of grid is required, or this much of energy storage upfront is required, and y amount of hydrogen storage is required. It would all depend upon case to case basis. It would all depend upon what is the overall requirement and the model of hydrogen usage for us, and how what are the things which other things which we are targeting, like the cost, the availability, the durability, the complexity of the complete system. So it's a combination of each and everything that is going to derive that, how much grid, how much storage.
Wonderful. Rahul, if you're on the call, would you like to ask the question yourself?
Uh, Sachinji, good evening. Thanks for very nice presentation. I wanted if you can highlight the CSP aspect for providing green power. This will reduce the embedded carbon from well to wheel. Yeah.
Absolutely. I perfectly align with your thoughts that particularly when we are talking of attaining 24 by 7. Am I think, Nishan, there is some disturbance there.
Okay, fixed it.
Okay. So particularly when we are talking of 24 by 7 options for us, uh, the combination of the renewable energy, or per se the PV or the wind hybrid kind of energy with CSP, is going to be one of the formidable combinations which can actually offset the requirements of the battery energy storage system in between. Parallelly, on the downstream side, also availability of concentrated solar power can actually assist and offset little bit of the hydrogen storage requirements. So per se, this is the area where as a country we should aim at. We should progress and try to find out the right and optimal blends of these technologies.
Wonderful, Sachin. I think the next question is from Rahul Sharma. I just noticed he just dropped out. But I'll read out his question for you. The conundrum between green and blue is still not solved, at least in the APAC region. People have started to feel green is too aspirational, and it's good to think of at least blue. Second question: where will the money come from, considering the appetite of consumers to pay the extra premium for green?
Absolutely. So both these questions are very valid, because the debate would continue. The debate between blue and green will definitely continue. Uh, CCUS, again, there are certain advantages, but yes, there are certain constraints, especially on the utilization side of CO2 per se. And the blue appears to be, you know, closer as far as, as compared to green, but it all depends upon what are the geographical constraints or the energy security constraints for different locations, particularly when I talk of certain areas where the natural gas is available. Definitely blue would be the easiest thing and the near term solution for them. But for a country like us, we are in any case importing natural gas, and we saw how the natural gas prices shot up, leading to reduction of the consumption as well as the increase of the overall cost. So the question is, where do we want to stand in the coming time? And that's where it would be the onus would be on the policymakers to decide that what path we have to take. Second aspect is about from where the money is going to come. Probably I may not be the right man to person to answer from where the money is going to come. I can only indicate at this point of time, whatever money is going to be available for these projects, we have to judiciously use and utilize that money. We should not be over assuming certain things, and then tomorrow we'll be seeing that the assumptions are backfiring. So that's where a role of us as an organization becomes very important to guide and navigate the clients in order to assume certain things which are more practical, which are primarily based on much more experience, and that it can help you to lower down the cost of overall production of hydrogen.
If I can add to that, blue hydrogen is actually, one of the risk classifications we had for green hydrogen, right? The cheap availability of blue hydrogen really affects the adoption of green hydrogen. And some Indian developers from in coming out of India, they've lost offtake agreements to blue hydrogen. Now, this is something we've passionately taken up with governments in Korea and Japan, and highlighted that, the very reason we are moving towards green hydrogen, we go against that when we adopt blue, right? They are trying to stop their dependence from fossil fuels, and getting blue hydrogen is actually still, going against these reasons. The second thing is, over time, green hydrogen will become cheaper, and over time, it's, within the next 5 to 7 years. And blue hydrogen projects, they have a longer gestation period, so governments and companies should not be encouraging investments in blue at all. And like Sachin reiterated, in India, we don't have abundant resources nationally. So, we don't have a blue hydrogen policy. Like one of, Sachin's colleagues used to tell me, India for a reason has no blue hydrogen policy. There's only a green hydrogen policy. But it is affecting Indian developers, especially those targeting the export markets. And this is something, we are advocating for within our conversation with these governments across the world. Next question is from CPCL Finance. I assume that's Chennai Petroleum. Which type of electrolyzer you would recommend for oil refinery, given treater and hydrocracker units as the recipient of hydrogen?
No, so it's again, it's not a question of recommendation and one solution fitting all. It's a question of addressing and bringing the challenges pertaining to different type of electrolyzer technologies, uh, to see that which is good for you or not good for you. It also combines with the fact that we can remove the traces of, I talked about KOH, particularly for the refining catalyst, but then it would come at a cost, first of all. And second thing is it reliable? Now these are the things, which we need to assess in terms of proper studies built around these narratives. And therefore, then only, anybody can say that which technology has the merit.
I have one of our senior advisors to the Green Hydrogen Organization here, Mr. Rolf. Rolf, if you're there, would you like to ask the question yourself?
Yes, happy to. Thank you. So, Saf, first of all, before the question, just a kudos. This was really brilliant. I learned a lot. So, and very going much into detail on water and things even go to a third. Was it the scope 3 emissions on green? So this was on electrolysis. Brilliant. Thank you. I know you're more of a refinery person, therefore I'm not sure you can answer. The question is, um, India has a huge debate on using hydrogen in ICE engines. What are your thoughts on that one?
Now, particularly coming from the oil and gas sector, we were also facing, working very closely with the OEMs. I know that, there are various automotive OEM guests attending this webinar. Uh, I personally feel, and it's about not a very generalized opinion, but combusting hydrogen, probably it may not be a good idea. Having said that, uh, we have to compare it on the specific fuel consumption basis, and definitely IC engines will be restricted by the so-called SI engine efficiencies, while the fuel cells per se are not going to be limited by the by those numbers. However, the ease of conversion, if we talk of, it all depends that what is the learning curve for the fuel cells. And with the electrolyzer technology maturing, and all of us are hoping that it is going to mature very fast, the learning curve of fuel cells is also going to fall. It is going to be expeditiously improved. So I see both these technologies going hand in hand for some period of time, but hydrogen IC engine more like an interim technology, filling up some kind of space, and ultimately we have to switch to the fuel cells. The requirement of the catalyst, per se, the noble catalyst in the fuel cells is also going to come down. The current densities are definitely going to improve. So these are the parameters which we should be carefully watching, and surely when the membrane technologies are going to improve, the catalyst coating technologies are going to improve. These things are going to fall in place where you will see the cost of fuel cells coming down. And then they will definitely be carrying the advantages in terms of efficiencies, making them much more meaningful.
Thank you.
Thanks very much, Rolf. We have one more question. Calculations, the cooling system, part of the balance of plant.
It is. It is part of the balance of plant. Again, the design aspects of the cooling system are, although they are considered while designing the system, but the assumptions were the things, which I was primarily questioning during my talk.
The follow-up question there is under scope 3 emissions, should we be considering accounting of 2 kg of carbon CO2 equivalent for per kg? Scope 3 is not being included, right?
They are not as you talk to any environmentalist, they will say every emission should be part of this. But from practicality, from practical point of view, adding these kind of complexities may not be helpful to the budding industry. So yes, you have to sketch the boundaries. What are your limits as far as CO2 emissions are concerned?
No, very rightly said, Sachin, because sometimes we get lost between where we started and where we are going, because every ton of hydrogen was producing nearly 10 to 12 tons of carbon emission, just for production, right? So we are coming from there to less than two. And for an emerging industry like this, we need to have, boundaries under which, we can operate more efficiently and scale up. One more question in the chat, and then we'll open it to the floor. I can see a hand raised. But Prasad Lime, if you're here, would you like to ask the question yourself? Well, okay, I will read out Prasad's question. For 1 kg of green hydrogen generation, how much kilowatts are generally needed? How can the power requirement be brought down to achieve cost parity? Very interesting question, Prasad. Power does account for a large chunk of the cost. So good thinking here.
Yes, but normally we talk of about 50 to 55 units to produce per kg of hydrogen. That is for low temperature electrolyzers. For high temperature, this number is relatively lower. I know there is a lot of research going on in order to bring down this electrical consumption to about 42, 43. But let me tell you one thing. It actually brings me to little more towards the discussion, which is much more meaningful in a sense that there are two aspects to look at the things. One is the capital investment cost, which all of us are knowing that where does it stand at this moment. And second one is how much an electrical units you are consuming in order to produce 1 kg of hydrogen. Now, our estimates say that the technology might be cheaper. You can end up buying a cheaper technology, but you can end up consuming more electricity. That is one aspect. The second aspect is you can go for an efficient electrolyzer, but that would be capital intensive upfront. So our calculations say for there is a relation 1 kilowatt hour of consumption, it actually relates to about 50 to $70 of the capital price of the electrolyzer. So there lies the break even. Each company can calculate that where what is the priority for them. And this answer to answer the second question, what is the power requirement, the parity, how to achieve this cost parity. Um, uh, there is thermodynamics attached to the complete field, that we cannot have lower than this much amount of energy to split water. And that is where we have to set our boundaries. Up to that limit, there is a scope of improvements in the material or the engineering design and all these factors. But below this particular limit, you cannot go beyond it. Then you have to take into factor in other process variations, like heat it up, use the energy from somewhere else, and all that stuff. But yes, you cannot move beyond below that threshold.
Thanks, Sachin. I'll open the floor to the audience. I don't know if Dr. Gopalakrishnan, if you'd like to ask a question.
Uh, well, you touched upon Sachin about the power requirement in case of this one. Would you like to throw some light on the life of this one, PEM or a alkaline this one? The second question is you shown some slide on some of the pre-treatment of the water required with this additional system. Is there any possibility of increasing the life of the electrolyzers?
So electrolyzer life is actually a function of at what voltage we are operating, so that the materials, ultimately it's the chemical conversion which is happening. Uh, so the durability of the electrolyzer life, it becomes a function of the operating parameters and the kind of materials which we are using. So as far as PEM electrolyzer is concerned, there are research efforts which are going across the world to increase the current density, because if we want to actually reduce the capital cost, and by increasing the current density, the throughput of hydrogen can be increased. But it would have its own penalties in terms of the durability of the electrolyzer. This means advanced level of research is required to be undertaken on the catalyst side, the way in which we are coating the preparing the catalyst recipes, the way in which we are coating those recipes on the membranes. As far as the alkaline electrolyzers are concerned, they are pretty robust, as the word knows. But again, the how much pressures we intend to get out of those systems, what is the what is those these process parameters are going to govern that how much life can be increased. But I assume and see that alkaline electrolyzers are quite mature in terms of durability. There are issues around corrosion because of KOH present as a medium, but that can be offsetted by the new technology which is upcoming, that is based on the AEM cycle, and therefore we can overcome those aspects.
Doctor, your mic is on mute. Sorry.
Thank you for explanations and detailed
Thank
knowledge.
you. Thank
Wonderful.
you.
Thank you, Doctor. We have GS Kapoor. If you'd like to speak, please.
Yeah. Hi, Sachin. Excellent talk as usual. My question is related to what GK Acharya just asked. So most of the manufacturers are giving electrolyzer life as maybe 10 to 12 years, maybe 80,000 hours to 100,000 hours. So what about so in our industry we are like used to having a system which works for 20 years or so minimum. So what about electrolyzer replacement cost? And how it is going to contribute to the cost of production of hydrogen in the longer run. Because nobody is going to put money for just 8-10 years and set up a green hydrogen unit. Any numbers you have with you?
Yeah. So I agree with the comments from your side, because that's what the assumptions what we are making in terms of designing the plants at this point of time, they are seeming to be little overstated, and we are assuming that the durability is going to be crossing these many hours. Having said that, the general consensus in the industry is that uh, about 25% of to 30% of the cost would be going as a refurbishment cost as far as electrolyzers are concerned, and I'm talking of the stacks. Again, it has so many riders attached to it depending upon what kind of technology we are talking of. Again, I laid lot of stress on the water requirements and the water quality, because we the as of now, the understanding is that the water is going to be of that particular quality, but if there are deviations from that front also, we are going to see that the stack deterioration can happen at a much faster rate, and therefore the overall cost numbers may change. So it actually is a combination of multiple factors which are required to be factored in while we are talking of and arriving at the cost of hydrogen per se for the project.
Thank you. Thank you, Sachin.
And thank you, Mr. Kapoor. And I think we should conclude this because we've overrun this by almost half an hour. And there's been a lot of engagement coming in. I want to sincerely thank everyone who've stayed on here, and also to Sachin for giving his time. And I think the questions that he's been answering with so much ease comes from a lot of effort he's put into his career and learning. So thank you once again. And with regards to our following webinars, we'll be in touch with you. We will continue having more of these sessions. We will do our best to have Sachin back on here again. And we will be launching a one-day masterclass very soon, coming in August. So, stay tuned for that as well. So with that, thanks everyone. And I wish you a lovely evening. Sachin, thank you once again. It was an honor
Thank you
having
very
you.
much. Thank you very much, Nishant, for having me here. And thanks to all the audience for patiently hearing as well as asking the questions.
Wonderful. Thanks, everyone. Goodbye.